Welcome to E-Padasala PG program for computer science students. In this model, we will be looking at embedded C code using arithmetic and logical processing. In this model, we will be discussing about the logical operators used in embedded C, as well as we will be discussing about the different data conversions done at embedded C, and we will be discussing the programs along with the data conversions, and at the end we will be discussing about how we will be sending the data and receiving the data serially without using any extra special functions in 8051. So, bitwise operations, when you are looking at the bitwise operations, we have AND, OR, exclusive OR and inverter. These are the operators which will be used when you are looking at each and every bitwise we will be operating it. So, as we know, the AND is one thing where if both are 1, then we will be getting a value of 1. So, that is the idea of using an AND gate. Here we have taken the data as 0x35, which says that the 0x says that it is a hexadecimal number, and 0x 0f. So, it says that 0f is a hexadecimal number. So, these two are ANDed, so that I will be getting a value of 05. Just see that it gets demonstrated over here. 3 is 0011 and 5 is 0110, 0101, and 0f is 000111. So, when I am ANDing it, these two are 1, so it is 1. So, these two are 1, this is 1, and all other places either 1 is 0. So, because of that this is 0. So, I will be getting a value of 0, 5, that will be my result. So, when I am looking at OR gate, these two hexadecimal numbers are OR together using this particular symbol, which says that OR is done. So, which is nothing but either one of the bit is 1, then it will be giving you the value of 1. So, when 0x04 is ORed with 0x68, we will be getting a value of 0x6c. So, 0x is telling you about it is a hexadecimal number. So, when you are looking at exclusive OR, the upward arrow mark symbol is giving you this particular operation. So, if I am writing it 0x54 and upward arrow mark with 0x78, then these two data are XORed together to get this particular value. So, just see that this is the demonstration where if both are similar, then it is 0, if both are different, then it will be getting a value of 1. So, by using this particular symbol, these two are XORed together and I will be getting a value of 2c. So, the next symbol is your inverter symbol, where if I am putting it, because it is inversion, we do not need to have two operands, only one operand when we are putting a inverter symbol before this, then 0x55 is inverted, so that we will be getting a value of 0xAA. So, the bitwise operations through logical operators, we can do all the bitwise operations using the logical gates, but when you are looking at the embedded C, some of the things which are all very special when you are looking, which will not be available in your normal C. There you just see that shift right, this has been done through this 2 greater than symbols. So, if I am writing it 0x9a, the shift right symbol along with the 3, then this data is getting shifted right by 3 positions. So, that is what it was trying to say. So, you just see that I am getting a value of 1001 because it is 9a, 1001, 1010, shifted 3 positions by right. So, it is shifted 3 positions right by 3 numbers. So, you just see that 3 zeros, first 3 zeros, after that 1, 0 0 1 1. So, 0 0 0 1 is 1, and you just see that the next value is 0 0 1 1. So, you just see that this is the next hexadecimal number which has to be supposed to be available at this particular position. So, now when I am looking at shift right by 4 times, you just see that 7 is nothing but 0 111 0 111, shifting right by 4 positions. So, 0 0 0, I am just moving it through this side. So, these 4 bits are zeros and this bit comes over here. So, 0 0 0 0, and you will be getting a value of 0 1 1 1. So, when you are looking at shift left, then you will be having something like 1 0 0 1, that means 9 6 1 0 0 1 0 1 1 0 1 1 0, then it is shifted left by 4 positions. So, when I am shifting it left, then you just see that this 0 1 1 0 comes to this position and 0 0 comes to this particular position. Just see that this is nothing but 6 and this 0 is coming over there, this all 4 zeros has to come over here. So, you just see that the whole thing is getting shifted by 4 positions, so that this goes completely and this particular nibble comes over here and the right side nibble will be 0 0 0. So, this kind of operations can be bitwise, you can shift the values by using these two symbols in embedded C. So, you just see that this is what we have explained in the previous slides, and has been done through your AND symbol. OR will be used this symbol and XOR is used by this symbol, and inversion is used by this symbol. This is actually a logical table. We have logical AND, OR, XOR and inverter we have covered in the previous modules, and this is just to demonstrate how the values we will be getting out of it. And this is an example program. We have the simulator embedded C can be run through different kind of simulators. Keil simulator is there, RAID simulator is there. So many simulators will work on embedded C codes. So, you just take any one of the embedded C simulator where you write this particular code and see that what will be your results. So, you just see that here P0 is equal to, because include reg51.h says that the reg51 library is included, so that it is directly telling that it is belongs to 8051 microcontroller. There because of that I can directly say P0 is equal to something, then it will automatically identify that this is a port 0. So, port P0 is equal to 0x35 ANDed with 0xFF, ANDed with these two values are bitwise ANDed, and the result will be pushed towards port 0. And just see that 04 odd with 68, these two are hexadecimal numbers which will be given at the port P1. So, when you are looking at 54 XORed with the 78, these two are hexadecimal numbers which the results will be placed to your P2. So, just see that we are using these are the ports as output ports, and the operation can be written as a expression, the logical operations can be written as a expression, and it will be pushed towards the output ports like P0, P1 and P2. If I wanted to invert it, just take it 0x55, 55 is inverted, so that AA will be there, that will be given to your P0, and you just see that this value is shifted right by 3 position and it is given at P1. This 77 is shifted right by 4 position which will be given at your P2, and your 0x is 6 is shifted by 4 positions and this will be given at port 0. So, whatever be the things which we have seen in the previous examples, that has been implemented using these statements with your embedded C code. Now, this is another example where 8051 C program to get a bit P1.0 and send it to P2.1 after inverting it. So, we will be reading a data from P1.0 and this is inverted which will be sent to P2 port 2 and 7th pin. This is port 1 and 0th pin. So, we will be reading a data from here, inverting it, reading it, and I will be sending it to this after inverting it. So, you just see that while I wanted to access this particular pin, then I will be in a position to declare it S bit in bit is equal to P1.0 upward arrow mark 0, which says that P1.0 is taken as given as in bit name, and this is of the data type S bit. So, that is the way we got P2.7 is also given as out bit, and it is the type special function registers bit. So, S bit is the variable with which these two are getting declared. So, bit variable is mem bit. Now, while 1, that means it is an indefinite loop. So, in bit is equal to mem bit. So, what will be the thing which we have read from P1.0 is moved to mem bit and it is getting inverted which is assigned to out bit. So, just see that this statement is for reading a bit from P1.0, this is to invert and it will be assigned to the pin 2.7. So, through this particular code we will be using inverting the thing which is read at P1.0 and it will be supplied to P2.7 output pin. So, when you are looking at your data conversions, we know very well if you are if you are pressing the key, we will be getting this as the value, but the system will understand in the ASCII value as 30, 0 key is 30, maybe 9 is your 39. So, when you are looking at these are the ASCII codes which has been given in Xcode. Now, this will be converted into a binary number. So, if this is the hex code, if it is converted into binary number, maybe I will be in a position to give this as the binary number, when BCD unpacked can be written like this way. So, 0 is written as 0 0 0 0 0. When you are looking at it is an 30x 30h is the equivalent value. So, that way if I am looking at 1, it will be written as 0 0 0 0 0 0 1. So, this is BCD, binary coded decimal, and if it is 9, it will be 0 0 0 0 1 0 0 1. So, now the ASCII codes from digit 0 to 9 is given over there. How we will be implementing this through code, that we will see. So, you just look at over there, 0 becomes 30 and 9 becomes 39 with respect to ASCII hexadecimal values. So, if you are knowing that this has to be converted, then we will be looking at this kind of program. You just see that this is a embedded C program where it converts a packed BCD to BCD number 29 to ASCII. So, 9 has to be separately written as code, and 2 is also written as separate BCD code. These two are packed together, so that we will be getting 29 as a whole number. So, now we will be including register 51.h to make it is 8051 controllers code. Then void main, there where unsigned character XYZ is taken, unsigned character my byte 0x29. Now, 29 is the input bit which has been given to my byte, which is a character type. Now, I have just my byte is ANDed with 0f. So, what it does over here is, because there is a 0 over here, the first 4 bits is getting first 4 bits in the sense 2, that means 0 0 1 0. So, that first number with the 4 bits is getting erased, that means ANDed with 0. So, it becomes 0. We will get 1 1 1 is ANDed with this 9. So, that we will be getting only the 9 over here. Now, P1 is equal to the x value which is 9, which is ORed with 30, hexadecimal 30. So, now these two are added together, so that I will be getting a value of 39 at P1. So, now I will be in a position to get that 39 is the BCD ASCII number for 9 which we have simulated. So, we wanted to convert this BCD to ASCII. So, 9 is converted into 39 now, which has been placed at P1. Now, we need to convert this 2 also. So, my bit ANDed with 0 F0, then this F is ANDed with 2 and 0 is ANDed with 9. So, 9 becomes 0, only 2 comes over here because it is ANDed with F. Now, because it is in the first position, so I will be pushing it to the right side. Because of that, I will be making up y is equal to right shift by 4 positions. So, that this 2 comes to 0 0 0 0 0, then 0 0 1 0. So, that way it comes. So, 2 value is given now. Instead of getting a 2 0, I am getting a 0 2 now. So, now this is ORed with this y is ORed with 3 0. So, that 2 is ORed with 30. So, that we will be getting a 3 2, which is the ASCII equivalent for 2, that will be supplied to P2. Now, you just see that P2 and P1 together we can get the bytes. So, just our program demonstrates converting a packed BCD 29 to ASCII, and the display of the output is given at P1 and P2 together. So, the next program which will demonstrate an ASCII number to packed BCD conversion. So, here you just see that we have given something like the value is 4 7. We wanted to convert ASCII value digits of 4 and 7 to packed BCD. That means, we wanted to have 47. So, now unsigned character W is equal to 4, unsigned character Z is equal to 7 is declared, and BCD type of character has been declared. Now, W is equal to W ANDed with 0f. So, that we will be getting something like your W is nothing but 4, 4 is getting your W ANDed with 0f. So, now we will be getting 0 and 4 is ANDed. So, we will be getting a fourth bit will be, you will be getting something like 4 over there, which will be shifted left by 4 position. So, that it goes to the front position, that means in 47 the 4 should come first. So, that I will be pushing it off towards the left side. So, that the first BCD value will be 4, the next we have to combine the 7 over there. So, because of that your 7 is ANDed with 0f. So, that we will be getting a value of 7 over there. Now, this 4 is already there, which is odd with this 7. So, that previously we know that 4 then 0 is there. Now, 0 7 is there with this particular value. Now, these two are added together. So, 4 0 with 0 7 is odd, we will be getting 4 7 as BCD byte. So, now this 4 7 is pushed outputted at port 1. So, this is the way this particular code demonstrates that the ASCII digits 4 and 7 are combined to make, or packed to make a BCD digit of 47 has been done through this particular program. The output is displayed in your P1 port. So, this is another example where we are generating a checksum byte. So, first we need to know how the checksum byte is generated with your read only memory. So, now if I have a number of data sets, then we have to add all the input bytes together and drop the carries. So, then after that with the sum, take the 2's complement of the total sum, which is nothing but a checksum byte. So, if I wanted to create a checksum byte, then I have to take up the data, whatever be the data I have been given in this particular code, this has to be added. After adding it, this has to be converted into 2's complement. So, that will be the checksum byte. Now, the program gives you that 25H, 62H, 3FH and 52H are the input data set. So, now I made it my data unsigned character my data array, where I have inserted 0x25, 0x62, 0x3f and 0x52. So, that all the 4 input data is pushed towards my character array my data. Now, I am initializing sum is equal to 0 and I am just declaring a character array which is x. So, with x ranging from 0 to 4 each and every time the loop is getting rotated. So, P2 is equal to my data of x. So, the first data is getting displayed at P2. Now, this my data of the first value is added with your sum and the sum is displayed at P1. Again I will be coming over there, x is getting incremented. Now, the next data is taken which is displayed over there, which is getting added with my sum. So, the now added accumulated sum is displayed over there. The same way all the 4 variables, 4 values of this particular my data array is displayed at P2 and each and every time it is getting added with sum. So, once the 4 values are added over here, the sum will have the added value of all these things. We never look at our carry, only we will be looking at only the summed values. Now, I wanted to take a 2's complement of it. So, complement of sum is done plus 1, which gives you the 2's complement, which has been done over here, which is assigned to your checksum byte. Now, P1 is equal to checksum byte. So, that our output is displayed at P1. So, this particular program demonstrates, if I am giving you different data sets, how to generate a checksum byte out of that particular input data. So, this is another example where your data set is converted from binary to decimal and ASCII conversions in 8051C. Just see that if I am having something like FD is the hex data which has been converted into decimal and display the digits with your P1, P2, P3, or you will be having something like FD is the data, I need to find out what will be the decimal values. So, how I will be, I will be extracting each and every decimal values that has to be displayed with assigned to this port 0, port 1 and P2. So, now we will be looking at 0x FD is given as the input to bin byte, then bin byte is divided by 10. So, because we are dividing by 10, it is a division is done and only the full number is moved towards your x. So, if I am doing it bin byte mod of 10, so that the remainder is pushed towards D1. So, the first digit is taken at D1 After that, whatever be the value which is already divided, so that which is again getting x is mod with 10, so that the second digit is also taken. Then for third digit, x divided by 10 is your third digit. So, if I am having 3 digit number, then it can be generated with this particular code. Now, this D1, D2, D3 are the values which will tell you about the first digit, second digit and third digit. Now, I am moving the value to P0, P1 and P2, so that the D1 is displayed at P0, D2 displayed at port 1 and D3 is displayed at port 2. So, now you just see that this code for binary to decimal conversion. So, when you are looking at this kind of operations, we will be looking at the memory space also. When I am looking at memory space, in the sense, we know very well with your 8051, we have only the RAM space of 128 bytes. So, at the maximum I can store only 128 bytes, but sometimes it may not be possible to store within this particular area. So, by the time we can use the code space also. If I am, because the system has the code space, we can either use the code space on chip RAM, or I can use external memory. So, I can make use of external code memory, or on chip ROM also we can use it, or we can use external either RAM or ROM for accessing or writing a data over there. This also can be controlled by us by writing it the code declaration itself. If I am changing the declaration, then I can make use of whether I can write it inside or outside, or with the code memory or with the data memory. So, all those things can be controlled by the syntax we are using it in the declarations. So, you know very well with your RAM, I have a bank 0, register bank 0, where the address is starting from 0 to 7. Then after that, individual variables can be stored after this 0 to 7, so that from 08 onwards, maybe if I am having a array element, after this individual variables, the array elements are getting stored. So, after this array element, stack will be appearing. So, with 128 number of data locations, we have to use all these things within that particular one, if I am using it only the RAM data space only. So, when you are looking at this kind of things, for example, if it is a 100 space, so 100 data, then I can use it with my RAM space itself. So, if I am using a simulator, by looking at the memory also, it is easy for us to identify where values are stored, that also we can visualize with your memory. So, in the simulator, if I am running this particular code, I can see very easily the 100 number of data is stored in my RAM space itself. Just see that this is to demonstrate where the code space, the contents of the code space, and to locate the values where it is accessing it, that we can monitor. So, you just see that this is include register 51.h and main void, where I have declared my data is a character array with 100 values, RAM space is allocated for that, and character xyz which is equal to 0. Now, x is ranging from 0 to 100, that means I am creating a loop with the values of 0 to 100 incremented by one value each every time. So, first z is equal to 0, now it is getting subtracted, my data of x is equal to z. So, z is equal to p1. So, each and every time I am just generating the z value within the loop, each and every time the value is generated and it is stored in my data. So, now you just see that when you are storing it, the RAM space is filled for 100 different spaces, that you can examine with your simulator where this is getting stored. And the z is also moved towards your p1, so that you can see that how the values are simulated, and that particular value you can see that in the RAM space. If I wanted to use something like 8052, there you can use register 52 header file also. There you can use the different RAM space also. In 8052 extra 128 bytes is also given, so that if I am using it 8052, then I have to include this as my register header file, and this will take extra 128 bytes to store your data sets. Sometimes you can use read only memory also to store data, that is also possible. You just see that this is an example program where all your data is stored in your main memory itself. You just see that I have just made it register 51.h, p1 is equal to h, p1 is equal to e, p1 is equal to l, p1 is equal to l, p1 is equal to o. That means hello is displayed with your p1 directly. So, the data itself is embedded in your code, so that it is not requiring any of the memory space. So, it is very simple, not requiring many space, it is very short also, but it is not flexible. Why? Because I have hard coded all the values over there, because of that the flexibility is not there, but there is no memory requirement for storing these values. Directly I am pushing these values towards my port 1. If I am looking at the same thing in a different way, I am writing it, where unsigned character my data hello, then the my data is an array which holds this particular one. Now I am rotating this particular loop for 5 times to display it. So, P1 is equal to my data of Z. So, each and every time H, C, E, L, L, O. So, that way the data push towards your port 1. So, the same program, same output we will be getting out of your P1, but now it is not hard coded, the data is given to an array. So, if I am given it to an array, then the data is stored in RAM and it will not occupy in read only memory. So, the RAM space is used to store this particular hello. This is another same kind of when you are looking at the same problem, when I am doing it in the other way around, where I just made it code unsigned character my data hello. So, what it says is it is unsigned character my data, but along with that we made it the another one word as code. So, what it says is the data is stored in the code memory, the ROM, the read only memory, the code space where we can use for storing this particular content. So, code unsigned character my data hello, and I will be putting it in a loop, so that each and every time I have read one character which is pushed towards P1. Only difference is this particular data is declared with the first word as code. So, because of that the data is stored in read only memory, but anyway the code and data are separately stored in that particular area. So, when you wanted to do serialization, that means it can be done very simply through code also. Just see that this is an example where I just made it S bit of P1, P0 is P1.0. Port 1.0 is given as a S bit variable P1 B0. So, this is a code to send out the value 44H serially 1 bit at a time through port 1 and 0th pin. So, LSB should go first. This is actually I am sending a data serially through pins P1.0 and the data is 44. This code demonstrates how I am serially sending this particular data. You just see that S bit of P1.0 is given as this variable name, and accumulator registers 0th pin is given as REG ALSB, and these two variable name is declared because the readability is also good. Now, I have given the data as 0x44 hexadecimal data, which is given to con byte. Now, I have given character x as one of the variable, accumulator is given con byte. So, the whole value is moved to accumulator. Now, 8 times the loop is getting repeated. So, first the register ALCB, which is nothing but ACC.0. So, for your 44, the last bit ACC.0 means the last bit of your accumulator is moved to P1.0. So, the LSB bit first has come over here. After that, ACC is equal to ACC greater than 1. That means it has been shifted right by 1 position, so that the second bit comes to my LSB bit. So, now again the loop is getting rotated. Because of that, the second bit which is available as ACC.0, which is moved to port 1 0th pin. Again it is moved by 1 position. So, the third bit is coming over here. Now, because of the rotation, the third bit goes to P1.0. That way the whole data which is given at your A is bit after bit it has been sent to P1.0. So, by using this particular code, I will be in a position to demonstrate a data which is given over there is sent serially through pin 1.0. In this module, we have discussed about the different logical operators, and we have written some C code for data conversion, and how we will be using the code space that can be monitored or that can be changed by making a different declarations with your embedded C code. We have demoed the data serialization through embedded C code. Thank you.